Uniform square sine of weight 40 newtons is suspended vertically from its top edge by a horizontal hinge as shown. The hinge is not frictionless. When the sine is displaced from the vertical by an external force and then released, it does not return to the vertical position. The maximum torque exerted by the hinge on the sine is 6 Newton meters. The sine is displaced by 90 degrees so that it is horizontal and then gradually released. At which angle to the vertical does the sine hang after release? Okay, so the maximum torque exerted by the hinge on the sine will be 6 newtons. Okay, and we know that the weight force is 40 newtons. And we know that the sine will have a length of 0.8. So the weight force will act right in the center over here, which is only 0.4 meters. Okay, so that's all the important information we have. So we need to find the angle between the sine and the vertical when the sine reaches equilibrium, because that's when the sine will stop rotating and it'll stop at an angle, so it won't be 0 degrees. That's why there's no 0 degrees options. After the sine is released, so the sine will be like this. This is how it starts off. After the sine is released, the weight force will produce a torque in the middle. So this is going to be a weight force initially. Cause the sine to turn. The sine will stop rotating if the weight force equals the maximum torque exerted by the hinge due to friction. So we know that torque exerted by the weight force is going to be equal to 6. And since the weight force always acts downwards, it's going to produce a weaker torque as the sine rotates, because if it's like this, the weight force is going to be looking like this. It's going to be looking downwards while the torque is going to be in this direction, and all the weight force is going to be acting as torque. So that's something to keep in mind. We want to find the component of the weight force in the direction of the torque. So let's imagine it's at some angle theta with the vertical. Draw it nice. And we have our sine. So find the component of the weight force that's in the same direction as the torque vector. Now we know that the theta is the same over here. That's going to be theta. And this is going to be a right angle triangle. This is also going to be. So since torque is on the opposite side of the force, so the opposite side of the angle, so torque is opposite theta and F is the hypotenuse. We know that the force acting in the direction of the torque is going to be F times the sine of theta, which means the torque is going to be equal to times F times sine of theta. So we know that the torque is going to be equal to 6. So we know that 6 is going to be equal to d times F times sine of theta. We can just solve for theta by making theta the subject. So we'll say theta divide 6 by df, and then take the sine inverse of that. Sine inverse of 6 over the distance is going to be 0.4 to be half. It will be half the length, and then multiply that by the weight force, which is 40. And this equals to, yeah, it's going to be equal to 22 degrees. Yeah, roughly 22 degrees. And one of the answers is 22 degrees, so it's going to be B. The answer will be B.